This is Transition Metal Chemistry, Chapter 21, Coordination Chemistry, Reactions of Complexes. In this chapter, we'll talk about three different types of reactions of transition metal complexes. The first type is ligand substitution reactions. The second type is redox reactions. The third type is the photochemical reactions. So we're going to look at the ligand substitution reactions first. And first, we'll focus on the chemical kinetics of this type of reactions. That means how fast these reactions can proceed. Section 21.1, rates of ligand substitution. Again, we focus on this word rates. We're talking about, again, how fast or slow these reactions proceed instead of the chemical equilibrium. We are not interested in the chemical equilibrium constant in this section. We're interested in the chemical reaction rates. Now let's look at a ligand substitution reaction here. So on the reactant side, you have a bond between M and X. X is a ligand, M is the metal. And Y is going to replace X. So on the product side, there's a bond between M and Y. And X is called the leaving group. Y is the entering group. I think in organic chemistry, you have learned this. You can have bromide or a bromide ion react with chloromethane and replace this chlorine and form this bromomethane and chloride. In transition metal chemistry, X and Y are ligands. So you can also say X is the leaving ligand, Y is the entering ligand. Transition metal complexes that undergo rapid equilibration are called labile. Transition metal complexes that undergo slow equilibration are called non-labile. So over here, labile means, well, this reaction is fast. Non-labile means this reaction is slow. Again, labile versus non-labile is regarding to the chemical reaction rates. They have nothing to do with the chemical equilibrium constant. Now let's look at this figure. This figure presents the lifetimes for exchange of water molecules in aqua complexes. We have transition metals, and we also have metals in the main group over here and over here. Those are the metal ions from the first two columns of the periodic table. So what does this mean? Exchange of water molecules. So we're just looking at this metallic ions. For example, this iridium 3+ ion. It's bonded to 6 aqua ligands. And then we're just measure how fast the solvent water molecules can replace those aqua ligands. So we're looking at the exchange between the aqua ligands that are bonded to this iridium transition metal center and the free solvent water molecules. And you can see the lifetime is 10 to the power of 10 seconds. This is really slow. And obviously, we can say, well, iridium 3+ is non-labile transition metal. Okay, this is non-labile. This is non-labile. Non-labile. Now, I'm going to give you a few examples of labile metallic ions. Well, lithium, sodium, potassium, rubidium, cesium, they are all in the first column of the periodic table. They are labile metallic ions. And why is that? First, well, they have only 1+ charges. That means they have smaller oxidation number than these two examples. That means there's going to be less electrostatic interaction between these ions and the aqua ligands. That's reason one. Reason two, they are not transition metal ions. You may imagine they do have d orbitals. Even lithium plus has a 3d orbital, right? It's just unoccupied. Even a hydrogen atom has a 3d orbital, but it's just they do not participate in typical chemical reactions. Similarly here, okay, they do have d orbitals, empty d orbitals, but the empty d orbitals of this main group metallic ions do not interact with the ligands effectively. There's no LFSE. There's no ligand field stabilization energy. And same here. If you look at magnesium 2+, calcium 2+, strontium 2+, beryllium 2+, they are in the second and beryllium 2+. They are in the second column of the periodic table. All right. And same reason, they do not have LFSE, ligand field stabilization energy. Their d orbitals do not effectively interact with the ligands. However, this beryllium 2+ has a longer lifetime than others. The only reason is this beryllium 2+ has a much smaller ionic radius than magnesium 2+, calcium 2+, strontium 2+, and barium 2+. And because of the small ionic radius, the electrostatic attraction between beryllium 2+ and water molecules is larger than all other ions in the same column. And also that's why magnesium 2+ also has a longer lifetime than calcium 2+, etc. Alright, now let's look at transition metal ions. This mercury 2+ appears here. So mercury 2+, it seems like, this one has a really short lifetime as well, and this is very labeled. How come? This is a transition metal. It does have d electrons, d orbitals. However, in mercury 2+, you have a d10 electron configuration. All right, mercury atom is s2 d10. I think it's 6s2 5d10. And now if you look at mercury 2+, it's just 5d10. So all 5 d orbitals are occupied, fully occupied. In this case, again, there's no LFSE. In this hexa aqua mercury 2 complex, 6 electrons occupy the lower energy T2G orbitals below the barycenter. 4 electrons occupy the EG orbitals above the barycenter. So the LFSE overall is 0. And that's why this mercury 2+ is a labeled transition metal ion. Now let's look at zinc 2+ and cadmium 2+. So if you look at this two, one here, they are also quite labeled with a short lifetime for exchange of water molecules. Again, for the same reason, they are both D10 structures, D10, right? And that's why there's 0 LFSE. That's why they have a short lifetime for exchange of water. Okay, now let's look at some other 3D transition metal ions. Let's look at this one. Manganese 2+, iron 2+, cobalt 2+, nickel 2+, vanadium 2+. They are all 3D transition metal ions with 2+ charges. So I would say they are moderately labeled. They are less labeled, of course, than this lithium plus, sodium plus, potassium plus. They are less labeled than calcium plus, 2+, strontium 2+. But they are more labeled, at least, than some other transition metal ions. So I want to say they are moderately labeled. Okay, they are moderately labeled with a lifetime in this range for those 3D transition metal ions with 2+ charges. Okay, from manganese 2+ over here, roughly 10 to the power of -7 second, to over here, vanadium 2+, it's about 10 to the power of -2 seconds. They are moderately labeled. The ligand exchange is relatively fast, although not as fast as this ions, but still pretty fast. Okay, now let's look at this 3. Titanium 3 plus, vanadium 3 plus, iron 3 plus. So overall, this 3 in general, they are less labile than 2 plus 3D transition metal ions. Well, obviously, when you have a higher oxidation number, the electrostatic attraction between these ions and the water molecules is going to be stronger than the 2 plus transition metals. So that's why those 3 plus transition metal ions is even less labile than the 2 plus 3D transition metals. And then we'll look at some other ions. Let's jump to this chromium 3 plus. If you look at chromium 3 plus, this is really non-labile with a really long lifetime. So over here it's about 10,000 seconds. It's above 10,000 seconds. So this chromium 3 plus is much less labile than iron 3 plus. Okay, they differ by a factor of 1 million. So 10 to the power 4, 10 to the power negative 2. And the chromium, if you remember, chromium, it's also in the among the 3D transition metal series. So why this one is so non-labile? Well, if you recall, chromium atom has a 4s2, 3d4 electron configuration, 6 valence electrons, 4s2, 3d4. Now this is chromium 3 plus. Okay, when you are looking at a transition metal cation, you need to remove the s electrons first. And furthermore, if you're looking at a transition metal complex, you need to move the 4s electrons into the d orbitals when you analyze the chemistry of the transition metal complex. So in this case, of course, in chromium 3 plus, you have just 3 d electrons. Now let's recall, in hexa aqua chromium 3 transition metal complex, you have an octahedral environment. The 5 d orbitals split into T2G and EG orbitals. There are 3 T2G orbitals. And these 3 d electrons in chromium 3 plus occupy this 3 T2G orbitals, dxy, dyz, dzx. And they have the same spin. And now if you look at the ligand field stabilization energy, well, this is D3. That means you have 3 times negative 0.4 delta O. You got negative 1.2 delta O. Ligand field stabilization energy. And 1.2 delta O is roughly 24,000 wave numbers. If I'm using the typical value of delta O, 20,000 wave numbers, and then you get 24,000 wave numbers. That's roughly 3 electron volts, or 300 kilojoule per mole. So I want to say the ligand field stabilization energy in this chromium 3 plus transition metal complex in an octahedral environment is roughly 300 kilojoule per mole. And even better, these 3 electrons each occupy one of the 3 T2G orbitals. So there's no electron pairing energy at all. So each of them occupy a different orbital. Okay, the third reason, all 3 electrons have the same spin. So we have the so-called negative exchange energy. Again, this is because when 2 electrons have the same spin, they cannot occupy the same spatial orbital. So electrons with the same spin can better avoid each other and thus have lower electron-electron repulsion. So for these reasons, chromium 3 plus, despite it's one of the 3D transition metals, is really non-labile. The hexa aqua chromium 3 complex is extremely stable kinetically. And now let's look at rhodium 3 plus. Let's look at iridium 3 plus. This is a 4D transition metal. This is 5D transition metal. We have learned that 4D and 5D orbitals are much more diffuse than the 3D orbitals. 4D and 5D orbitals can overlap with the orbitals on the ligands, and that makes delta O really large in the octahedral complex of those 4D and 5D transition metals. Over here, again, let's just go over this analysis. If you have D0 or D10 complexes, their ligand field stabilization is 0. So supposedly, you're going to observe really fast exchange of their ligands, and we'll call them label, with two exceptions, beryllium 2+ and magnesium 2+. They have small ionic radius, so they have I would say over here, a longer lifetime for exchange of water molecules than some other D0 and D10 elements. Okay, again, this is because small ionic radius. And then if we look at the 3D transition metal series, the metal ions with 2+ charges are moderately labeled, so they are pretty labeled. And metals with 3+ charges are less labeled, just because of the stronger electrostatic attraction between metal 3+ and the ligands. And then in the 3D series, you also need to look at the electron configuration carefully. If you have D3 or low spin D6, they have really large LFSE and thus are non-labeled. So I'll give you this example here, Chromium 3+. This one has a D3 electron configuration, and all three electrons occupy the lower energy T2G orbitals with a delta O of -1. With a LFSE of 1.2 delta O. That's pretty large. What about low spin D6? Well, in this case, you have all 6 electrons that occupy the lower energy T2G orbitals. So the ligand field stabilization energy is 6 times -0.4 delta O. It's -2.4 delta O. So it seems like we have even more LFSE here, but don't forget, in this low spin D6 transition metal complex, you have 3 pairs of electrons occupying the same d orbitals. So in dxy you have 2 electrons, dyz 2 electrons, dzx also 2 electrons. So there's going to be additional electron repulsion because they are in the same d orbital. There's a stronger repulsion, and we use a parameter p to denote this additional repulsion. So in the low spin D6 complexes, the true ligand field stabilization energy is actually -2.4 delta O plus 3p. So you do need to know the values of delta O and the value of p to estimate the LFSE more accurately for the D6, low spin D6 situation. D3 is easy. Again, D3 is easy. There's no electron pairing energy. So 4D and 5D, again, they have larger d orbitals that can overlap with the ligands better than 3D metals, and then they have large LFSE. It's just their delta O values are much larger than that of a 3D transition metal. So 4D and 5D transition metal ions are non-label ions. And 4D and 5D transition metal complexes are almost always non-label, unless you have a really weak field ligand such as ardito. Okay, and then we'll have to look at that situation differently, more carefully. Chelate complexes are non-label, mainly due to the entropic effect. So let me give you a simple example, EDTA. So when a transition metal center forms a complex with EDTA, there are actually 6 bonds. It's a non-perfect octahedral environment. The transition metal is bonded to 4 oxygen and 2 nitrogen. It's not a perfect octahedral, but still we can use the same molecular orbital energy diagram to analyze this, right? But in the end, it's not really about the energy. In this case, for chelate complexes, they are non-labile. They are kinetically stable, mainly due to the entropic effect. So now let's imagine when a iron 3 transition metal ion is bonded to EDTA, forming 6 bonds with the same EDTA 4 minus anion. Now, how can you have 6 other ligands from the solvent, for example, aqua ligands, simultaneously replace all 6 bonds between this iron 3 and EDTA? Alright, so statistically, it's very, very unlikely for 6 separate ligands to replace this EDTA simultaneously. And that's actually the entropic effect. In this kind of reaction, when you have 6 aqua ligands to replace this EDTA, the transition metal, the transition state structure. So if you learned chemical kinetics before, there's a transition state between the reactant and the product. The transition state has a very, very low entropy, and it's unfavored due to its low entropy, and that means the reaction rate constant is extremely small. If you have learned the Irene equation to calculate the reaction rate constant, it's this. The reaction rate constant is kBT over H times e to the power of negative delta G double dagger over RT. This delta G double dagger is the Gibbs energy of the transition state minus the Gibbs energy of the reactant. And if the transition state has a very low entropy, and then it has a very large delta G, very large Gibbs energy, that makes delta G double dagger, the Gibbs energy of activation, really large, and that results in a small reaction rate constant. Now, a definition for this nuclear facility. Nuclear facility is the rate of the attack on a complex by a given Lewis base. Actually, it's going to be a ligand relative to that of a reference. The reference is also a ligand. So, for example, you can just use a ammonia ligand to replace a water ligand, and then we can measure the relative rate between this exchange rate. You can use ammonia to replace a water, and then you can use a water to replace a water, right? So, the reference ligand is referring to also the entering ligand. So you're comparing 2 entering ligands. All right. Again, if you have a hexa aqua transition metal complex, we can use a ammonia molecule to replace one of the aqua ligands. We can use a water molecule to replace one of the aqua ligands. And then we can use, for example, 1,2-diaminoethane to replace 2 aqua ligands. We can use EDTA to replace all 6 aqua ligands. And we're just making comparison between the chemical reaction rate constants for those different entering ligands. All right, so we have the same leaving ligand. Okay, that's the same. And then we use different entering ligands to replace the leaving ligand and compare the reaction rate. What's the relationship between nuclear fissility and basicity? Well, this relationship is equivalent to the reaction rate constant versus the equilibrium constant. And it's equivalent to kinetics versus thermodynamics. Again, I'm going to give you this example. this hydrogen and hydrogen and oxygen can react to produce water. The equilibrium constant is large, but the reaction rate constant is really, really small at the room temperature. All right. Now, finally, I want to explain this basicity here, why it's called Lewis base and Lewis acid. Okay. Lewis acid, they accept electrons. Lewis bases give electrons. So when you form a transition metal complex, the ligands give electrons to the transition metal and form a bond. Okay, it's a donor-acceptor bond. The electron donor is the ligand. The electron acceptor is the transition metal. So that's why we call the transition metal center a Lewis acid. We call the ligands Lewis bases. So that's why we have Lewis bases here. And again, this nuclear fissility is just a measure of how fast a given ligand can swap out a previous ligand that's bonded to the transition metal.